Hello everybody, today we are talking about geologic time, how we know what geologic time is, how old is the Earth, also how we know what's happened in the geologic past. So we're starting out with looking at the geologic time scale. Two different illustrations on the screen. One is a detailed view of the geologic time scale, and the smaller one on the left is actually just looking at the eons in the geologic time scale. And the eon is the largest division of time in the geologic time scale. Generally, scientists think of 4 eons, but in reality, what we deal with on an everyday basis in the scientific community is just the 3 eons. And the 3 eons are the Archean, and then we also have the next one, which is the Proterozoic, and then the Phanerozoic. And we are currently living in the Phanerozoic eon. And the Phanerozoic eon goes back to 543 million years ago. Previous to 543 million years to 2,500 million years ago, so from this time to this time, 2,500 million years being 2.5 billion, that was the Proterozoic eon. Prior to the Proterozoic, and largely all of geologic time prior to the Proterozoic, is going to be the Archean eon. Now, if we take the Phanerozoic, and I can expand it out from here all the way down to here on this illustration on the left, this is all the Phanerozoic eon here. And then prior to the Phanerozoic, again, we have the Proterozoic and the Archean. So in the Proterozoic and the Archean, the only thing significant that we see in geologic time is the very first earliest fossils came sometime early on in the Archean. And then there's a slight change in the way the atmosphere looked at about 2,500 years with the beginning of the rise of oxygen. And that whole eon is the Proterozoic. And what defines the difference between the Proterozoic and the Phanerozoic, so the Proterozoic here and the Phanerozoic here, is the very earliest shelled fossils. Fossils are the very earliest shelled animals, and that happened at about 542 and 543 million years ago. So how do we know that happened? We know that looking at the rock record, places where we can excavate down into the earth in sedimentary rock, or at the Grand Canyon where the Colorado River has excavated it. We can see the layers of that rock. We can age the rock using relative timescales and radiometric dating, which we're going to show you in a few minutes. And we know the age of the rock, and where we see the fossils first appeared, and the first shelled fossils, meaning little creatures with shells on them, like trilobites, for instance, is something we see in the rock record. They first appeared at 542 million years ago, and that creates that break in the geologic timescale from the Proterozoic to the Phanerozoic. Now, the Phanerozoic has a great number of other events that we see in the rock record, and that's why we have these further breakdowns of eon to era to period to epoch. And we are currently in the Cenozoic era, which means early life. The Mesozoic era was middle life, and the Paleozoic era was actually what was known as early life. Within the Cenozoic, we have periods, the Tertiary, the Quaternary, and then those are further broken down to the Paleocene, Eocene, Oligocene, Miocene, Pliocene, Pleistocene, and what we are now in the Anthropocene, or what actually known now as a Holocene, but some people call the Anthropocene, meaning the period in which man had an impact. So the Cenozoic is early life, Mesozoic is the middle life, which includes the Cretaceous, the Jurassic, and the Triassic, which, as we know, is the time of dinosaurs, and the Paleozoic, and that's when the first shelled animals came out as amphibians, and then reptiles, and then the development of reptiles into the later life. So the geologic time scale broken down into eons, eras, periods, and epochs. And we know that they exist, and we create the divisions based on what we see happening in the rock record. So the division between the Proterozoic eon and the Phanerozoic eon is that first shelled animal. When we're looking at the Paleozoic era, breaking it down from the Cambrian to the Ordovician, well, the Ordovician occurs at 448 million years ago when the first fish are seen in the rock record. And then from the Ordovician to Silurian is when we see the first land plants. So we had nothing on land in the rock record until about 444 million years ago, the first land plants, and so we call that the Silurian. And then the first amphibians came out at 359 million years ago, and that's where we went from the Devonian to what's known as the Carboniferous. And the Carboniferous is when we had significant development of carbon, or fossil fuels. And so we have the Mississippian and the Pennsylvanian, and it goes on and on. The Permian to the Triassic, that major distinction between the Permian and the Triassic going from Paleozoic era to the Mesozoic era is one of our very significant mass extinctions that we see. Just the same way as going from the Cretaceous or the Mesozoic to the Cenozoic here, that occurred at another mass extinction, the extinction of the dinosaurs, which happened about 66 million years ago. So currently we are in the Anthropocene or the Holocene, depending on how you want to call it, of the Quaternary period, of the Cenozoic era, of the Phanerozoic eon. And within that, the last epoch, the Anthropocene or the Holocene, really only goes back about 10 or 12,000 years. And it starts at the end of the last ice age. The last ice age, the Wisconsin Ice Age, ended about 10 to 12,000 years ago, and that began the next epoch of the Anthropocene or the Holocene. All right. Down to our next slide. So there is a lot here on this slide. We have three different graphics. The Phanerozoic climate change. I also have on the right, it's showing the geologic time scale and sea level, and the very bottom is a sea level chart, but only in the last 200,000 years, which would be the Pleistocene. So let me just sort of give you an idea of how geologic time works. 200,000 years, the Pleistocene seems like a lot. And the Pleistocene actually goes back to 1.8 million years. So this is really only a tiny slice of the Pleistocene. So get my pencil up here for you. So this slice right here represents just about one line right here where it says Pilo and Pleist. That's the Pliocene, the Pleistocene. So that gives you an idea just how deep geologic time is. Going back, this is 543 million years. But remember, it goes back another 4,000 million years beyond that when we start talking about the Hayden and the periods before the Precambrian. Nonetheless, what we're looking at here is the climate change to the Phanerozoic. All right, so it goes back 542 million years. So this point right here is this point right here. All right, and then this is just the last 200,000 years. So what I want to show you is using ice cores from the Vostok location, which is on Antarctica, drilling down into the ice, we've got information that gives us a very good idea of what's happened in the temperature, the carbon dioxide, the methane in the atmosphere, and also an oxygen isotope that gives us a very good indication of temperature as well. So that's where we got this data from, the ice cores. And this red line is going to be your longer term climate, and then the blue line is going to be the short-term climate. So the red line sort of smooths things out. So when we talk about the Jurassic and the Triassic and the Cretaceous, here is the Triassic, here is the Jurassic, and here is the Cretaceous. They used a K because they'd already used the C back for back here. So this time frame, the Cretaceous and the Jurassic, the time of dinosaurs, we can see that the general temperature trend was up, and it was very warm. And when you think about the dinosaurs and you think about swampy, steamy areas with brontosaurus hanging out eating their seaweed, yeah, we think about a very hot period. So we know that Cretaceous was one of the very hot periods in Earth's last 500 million years. And we can look at the sea level, the indications of sea level that we get looking at the rock record, and we see that in that Jurassic to Cretaceous period, the sea level was up significantly, and then it fell after the Cretaceous into the Oligocene. But then we had this period of very low sea level, very high sea level, very low sea level, very high sea level, very low sea level, and then sea level coming back up. And that's what we're looking at in this bottom chart down here, is that fluctuations in sea level in the last 200,000 years. And looking at temperature data, we can match up very nicely the fact that when the temperatures on Earth were very, very warm, the sea levels were very, very high, meaning most of the ice in the glaciers and ice sheets had melted, and that caused sea level to go up. All right, and then when sea level, when temperatures were lower, like for instance in this period from 140,000 to 180,000 years ago, we have sea levels being much, much lower here and here, because all of the water was locked up in the ice sheets, and so our sea level dropped. And so essentially looking at different types of data, we can correlate and see that the climate of the Earth, if you consider this to be the current level climate right here in terms of temperatures, the climate of the Earth has varied dramatically over geologic time, and really significantly it's been warmer than it is right now for much of geologic time. So much of the past, even when it was quite warm, quite hot, the Earth's climate has been warmer than it is right now. When people talk about climate change and man-made or anthropogenic climate change, one of the big reasons why we think that we're pushing the climate warmer is that in all these time periods in the past when temperatures were quite a bit warmer, greenhouse gases were not significantly higher than they are today, meaning we have pushed greenhouse gases much higher in the last 200 years, and the expectation is that the temperature of the Earth is going to respond to that. The temperature of the Earth is actually going to respond to those additional greenhouse gases. All right, now we can see the same view in terms of geologic time with sea level. Then I've added a little map there of Florida. And what you're looking at with the map of Florida is the difference between sea level from now to 20,000 years ago to 5 million years ago. And it gives you an idea of how sea level has fluctuated as ice ages have increased and then decreased. So an ice age being a glacial period, and then between ice ages, the warmer periods known as interglacials. So what you're looking at, of course, is the gray is what Florida is now, what we're accustomed to seeing with Florida now. This area, what you're seeing, this kind of much smaller version of Florida, that is from about 5 million years ago. And in between 5 million years ago and where we are now, this dotted line goes back about 20,000 years ago. So where is that on our geologic time scale? Well, if we look at Florida now, this is sea level at present, but also we know that sea level has been rising over about the last 200 to 100 years. And that's just from measuring tide gauges and then also satellite altimetry. It's telling us that sea level is coming up several centimeters a year, as a matter of fact. If we go back to the early Pliocene, this point right here, this much smaller one, that early Pliocene is going to be right about here, where we are talking about there being a much warmer period. So this is the early Pliocene right here, and a much warmer period. And because it was warmer, all right, then the ice in the ice sheets melted, and sea level came up to this much higher place in Florida. And we can see that in the rock record. We can see where sand dunes are inland, and those sand dunes represent when sea level was much higher. The next one we're looking at is the late Pleistocene. So that's the very end of the last ice age, when there was a lot of water that was locked up in the ice, and that's right here. All right, that's the end of the last ice age, and when all that water was locked up in the ice, Florida was this wide, and that is kind of the edge of what's called the Florida platform, and we know that the whole platform of Florida was that wide. And then, of course, from that last Pleistocene ice age, sea level has warmed, and since then our sea level has increased to our current day location, what you typically think of as Florida. But scientists also know that sea level continues to rise, and with sea level rise, we may once again see an inundation of the lower land areas in southern Florida and even coastal parts of Brevard and Volusia County. So a good indication of the climate of the Earth over the last 542 million years, how it's affected sea level, and then really good maps of the last 20,000 years, even the last 5 million years, of what's happened with Florida and sea level. So how do we know all this is going on? I mentioned ice cores already, and we also have sediment cores. And there's pictures of both of these with your sediment core here and your ice core here. By coring down into sediment in lakes, large lakes, and even the ocean, you get a very good history of the Earth. And the different sediments have different data on them that record different periods of the Earth and what was going on with the Earth. This is the drawing of a sediment core going back about 200,000 years, 20,000 years that is. But what's amazing is these ice cores down in Antarctica. The ice over Antarctica is about 3,000 to 4,000 meters thick. It is very thick. It represents ice accumulating over many, many, many thousands, tens of thousands, and even millions of years. In the end, we're looking at an ice core that's going to take us back some 500,000 years, looking at what's going on in the Earth. Again, they're around 3,300 meters deep, going back about 450,000 years. And looking at that, we see lots of different data. The gray area here, this is oxygen isotopes, and oxygen isotopes are very exact proxies for the temperature on the Earth at the time. The second thing we're seeing is the amount of carbon dioxide, check that, the amount of methane, CH4, not CO2, the amount of CH4. The third thing we're seeing here, this is actually the amount of carbon dioxide that's blue that we're seeing right here. And then we also have the temperature, this red, that is going to be the temperature. So this Volstock ice cores are tremendous at giving us information on what's happened in the atmosphere for the last 500,000 years. And we can see that CO2, here we are here, is significantly higher now. Let me give you a different tool here. There's our CO2 levels right there, significantly higher. Over the last 500 and almost 500,000 years, we've never had CO2 levels that were this high. And our temperature is only now responding. Our temperatures are going up as well. But you can see how CO2 levels go up and then temperature follows. CO2 levels go up here and then temperature follows. And CO2 level comes down and then temperature follows as well. And these ice cores are one of the best ways that we know what the climate has been like in the last 500,000 and then even the last 500 million years, is by looking at these types of ice cores in this data. In terms of knowing how old the Earth is in general, one of the tools that we use, of course, is going to be radiometric dating. And in terms of radiometric dating, that is essentially looking at different types of radioactive materials that are in the Earth's crust and dating those rocks. All right, so on this slide, we get a basic image of how radiometric dating works. When a rock is formed, whether it's going to be formed from metamorphic rock or from igneous rock, when it's formed, when it cools, elements form when it cools. If those elements happen to be radioactive elements, and what a radioactive element is, it's just an unstable element. It has too many protons, too few protons. It wants to become stable. It wants to have the right amount of protons. So those elements change to more stable elements. And that change from an unstable element, called an isotope, to a more stable one, that is going to be that's basically radioactive decay. And that's the change from one to the other. And it releases energy and releases heat when it does it. But the way we can use that radioactive decay to age rocks is that what we've learned is that the progression of radioactive decay, while random, has a very specific time frame. And that time frame is what we call a half-life. So let me go back and clear this for you. And the half-life of radioactive decay says that when a rock is formed, again, that's our zero. So I'm going to call this time 0. That's our 0. When the rock is formed, all of the unstable elements are in place. If we counted these, let's say there's 20 of those. Uranium-238, the original isotope. Well, those isotopes are unstable. They don't want to be uranium-238. They want to change to a more stable isotope, or lead-206, which is the final product. The time it takes 1/2 of those to change from the unstable uranium-238 to the stable lead-206 is the half-life. That is the half-life. Let me just say half. I think we'll go ahead and write it all. That is the half-life. And the half-life, it just so happens, of this is very long. It's about 4.5 billion years. So when we find rock, we can go into a piece of rock, a sample of rock, and we can count the number of isotopes of uranium and the number of isotopes of lead. And based on the proportion of one to the other, we know how old that rock is. If another half-life occurs, another 4.5 billion years, now there is 25% of the rock is uranium and 75% of the rock is going to be lead. Another half-life goes by, only 12.5% of the rock is uranium, and that means 87.5% of the rock is lead. Each half-life changes the proportion of the parent isotope to the daughter product. The parent isotope is the original. What it decays to is the daughter. And that is the way we radiometrically date rocks. Now, we can't radiometrically date sedimentary rocks that have fossils in it, but we can use metamorphic and igneous rocks around the sedimentary rock to get an idea of exactly how old those sedimentary rocks are. So this is a basic look at geologic time, what geologic time can tell us about when different animals arrived on Earth, different things that happened on Earth, but it can also tell us about the climate of the past Earth, including the temperature and the sea level of past Earth.